All right, ladies and gentlemen, welcome to the last section for trig and pre-calculus. This is the 10.3. This is like the third of the three big things that we learn in the calculus. So we've kind of touched the surface with derivatives. We've touched the surface with, the integrals. And we're going to start touching the surface for limits. And then next year in your calculus class, we will dive in deeper in all three of these aspects. So let's go ahead and take a look at this. Ultimately, our objective is just to be able to evaluate limits of functions. And what this is basically asking is, what happens to my function as we get really close to an x value? Some are easier than others. Some really have to make you think a little bit. We're going to be looking at all sorts of different types here. So we're going to start off with just limits first. In this particular question, I want to, if I get my pen going here, I want to find the limit as x approaches 3 of this function x squared plus x minus 3. And it's basically asking what is happening to this function as x gets closer and closer to 3. And we know this function to be some sort of quadratic. Let's see, -1, so something over here, I believe. Maybe. I don't know. It's a quadratic. And what I want to know is what is happening to this function? Basically, what is the y value getting closer to as we get closer and closer to the x value of 3? Now, in this case, all I have to do is plug it in because I want to know what's happening. And 3 is not, there's nothing wrong going, there's nothing bad going on at x equals 3. So all we have to do in this case is plug it in. And this isn't always the case, but in a few cases like this, and I'll explain it a little bit more depth in a few minutes. Oops. If I plug 3 into this function, I get 9. That means the limit of this quadratic function as x approaches 3 is equal to 9. And basically what I'm saying is the x equals 3 is not a discontinuous point. The function goes through that point at 3, 9. So another one like this would be the limit as x approaches 0. Now, if you were to graph e to the x times the cosine of x, neither of these functions have any problematic points. I can plug, basically saying the domain is all real numbers. I can plug anything into e to the x, and I can plug anything into cosine of x. So 0 is not a problematic point. So again, all I have to do is plug it in. And e to the 0 power is just 1, and cosine of the 0 power is also 1, and therefore the limit as x approaches 0 is 1. And you can plug in any number here. It doesn't matter what it is. You'll still get an answer. It won't be 1, but it'd be dependent on what x value you're getting close to. Here, I want to kind of throw you guys a little bit here. If I wanted to take x approaching -1, we really do have to look to see, is -1 an okay number in this function? Well, this is x minus 1 over x squared plus 1. And if I plug -1 into the denominator, I do not get 0. And therefore, it's okay to just plug in. So I can say, okay, -1 minus 1 over -1 squared plus 1. And I get -2 over 2, which is -1. So as x approaches -1 for this function, the y value approaches -1. Now, yes, if I just plug in 3, I get 9, so it's actually the coordinate 3, 9, that sort of idea. But we're really talking about what happens as x gets really, really close to these values. Now, we call these three types, or these three questions, direct substitution types. because they're not points of discontinuity, means the function is continuous at these points. And I can just plug it in. Now, that's not always the case. Sometimes functions are not as nice as this. And what we're going to really look at is starting to look at problematic points. So there are some properties of limits on page 817 of your textbook in the green box. And these are going to be coming in handy here in just a couple moments. The first useful identity that we're going to look at a little bit later, and we're going to use a little bit later also, is the limit as x approaches 0 of the sine of x over x is equal to 1. Now here's where it gets interesting. If you plug 0 into this equation, you can't plug 0 into a denominator. As much as you want to, you can't. However, if you were to graph this function does this, something along this line. However, it has an open dot right there. It has a jump. But if we really look at this, as we get closer to 0 from both sides, it really does look like it approaches a y value of 1 on your graph, and that's what we're going to go with here. We're going to use this in the next couple problems, this first little identity, and we're going to use those green properties, or those properties in the green box, as we move forward on these next three problems. So the first one here is, I want to find the limit as x approaches 0 of this function here. So I'm finding the limit as x approaches 0 of x plus sine x over x. And we're going to use some of our properties here. First, you have to understand that x plus sine x over x can be written as x over x plus sine x over x. Now that you might understand why there was a reason I said something about this identity. So this is going to equal, using our sum rule for limits, I can say the limit of a sum becomes the sum of the limits. Now this one, x over x, is just 1. And we know that this is our identity right here. The limit as x approaches 0 of sine x over x is 1. And then some people have a little bit problem with this because there's no x value here. Well, the limit of a constant, 1 is just a constant. The limit of a constant, doesn't matter where the limit goes to, is always 1. So we get 1 plus 1 is 2. So therefore, the limit of this function is 2 as x approaches 0. Let's kind of look at the same thing here. Again, we are still looking at x approaching 0. And we're going to do basically the same thing. The limit of a difference is actually the difference of the limits. So I can say it's the limit as x approaches 0 of 1 over x squared minus the limit as x approaches 0 of, oh, whoops, I did this one wrong. Sorry, I don't want to do that. My fault. Try that again. Not paying attention to myself as I go. 1 minus cosine squared. I knew this is where I wanted to go and I forgot. 1 minus cosine squared is sine squared of x. So I can change 1 minus sine squared into, 1 minus cosine squared into sine squared. And then we have a power rule for limits. Since this is squared and this is squared, I can say the limit as x approaches 0 of sine x over x squared, because this whole fraction here was squared, so I can square the whole limit. Well, again, this is my identity. The limit of x approaching 0 of sine x over x is 1. So I get 1 squared, which is 1. So the whole limit of this function is 1, just using a little bit of manipulation that we've done in previous chapters. One more here. This one kind of goes along the same lines as the second one there. Basically, we can look at this as radicals if you want, as a root rule. The number 7 rule on here says that the limit of two roots, you got to understand that first of all that this really is the cube root of the entire fraction. So I can say this is the cube root of the limit as x approaches 0 of sine x over x, and we know that that limit is equal to 1, so we just get the cube root of 1, which is 1, and done. All right, so in these cases where you're looking at these type of problems, you need to manipulate the thing into somewhere along the lines of getting sine x over x and being able to split it up using our properties in the green box. Okay, one of the last big things that we're going to cover here is single-sided limits. All of the functions that we dealt with so far, like sine x over x, where sine x over x does this, and when we come in from the left-hand side, it comes up to 0, or sorry, up to 1. And when we come in from the right-hand side, it also comes up to a 1, and we call this a two-sided limit. Both sides of 0 approach the same number. But that's not always the case. We have these nice functions called piecewise functions. I don't know why I said recall, because we haven't gone over this yet. What we need to do is we need to actually define this. If I was to say, let's take the limit as x approaches 0, but I don't want to think of it as approaching 0 from both sides. I want to think about it as a single-sided. So if I want to come in from the left side, well, everything to the left is all negatives, so I need to come in from the left side. So I put a little negative sign up and to the right of this, of whatever number is down here. If I wanted to take the limit from the right side, you guessed it, we get a plus sign. So what this says is, let's take the limit as x approaches 0 from the left-hand side. So if we looked at that sine x over x again, if we approach from the left-hand side, it's 1. If we approach from the right-hand side, it's also 1. And our little property that we get is if the limit from the left is equal to the limit from the right, then, so this is kind of our, oops, sorry about that. If the limit from the left is equal to the limit from the right, then the limit as x approaches 0 exists. And that's very important for us. And that's actually what goes to that one problem we did on the worksheet a while ago, talking about the limit as h approaches 0 of the absolute value of h over h. If we were to take this as look as h approaches 0 from the left, and this is how I described it, but not in these words. If we approached from the left of absolute value of h over h, you actually get a -1. We're looking at negative h values. But if we look at the limit as h approaches 0 from the right, we get a +1. And because those two things are equal, we would say this does not exist because you can't have two different limits. All right. Let's go forward here. Go forward. All right. So here's what we want to do. We want to find the limit of f of x as x approaches some number from the left and from the right. And you could probably guess that we're going to be looking at what happens at 2. So we want to approach 2 from the left-hand side, and we want to approach 2 from the right-hand side. And we want to see if they come out equal. And they're not always going to. Piecewise functions don't, they rarely ever touch at the same points. There's usually a jump in there. But all we have to do is we have to go back to thinking about direct substitution in some of these cases. As x approaches 2 from the left-hand side, we're going to use the left-hand side function. The negative x squared plus 4x minus 1 is left of negative 2. So along this function, whatever it might look like, we could figure out if we really wanted to. Let's say it looks like this, and then 2x minus 3 looks something like this. There's going to be a jump, but from the left-hand side of 2, it's following this line coming up to this y value. And as we approach from the right-hand side, coming in from the right, the function is reaching this y value in the other function. So let's think about just first of the limit as x approaches 2 from the left of f of x. It really comes down to just knowing what's left of negative 2. That's less than negative 2. So I need to use the left side function, and I get to plug in negative 2. So I get negative 2 squared is 4, so this becomes a negative 4 because the negative there. 4 times a 2 is 8, and a minus 1. So here I plugged in x equals 2, I squared it, I got the negative. I did a 4 times 2, got 8 minus 1, and I get a 3. That means the limit from the left is equal to 3. So let's see what the limit from the right is. So in order to find the limit from the right-hand side, I need to use the right-hand side function, and that's everything bigger than 2. So I get to use this one. I get to say, okay, plug in 2. I get 2 times 2 is 4. Minus 3 is a 1. Are these two things equal? Of course not. That means if we were to ask this question, what is the limit of f of x as x approaches 2? Well, because it's different on either side, we're going to say it does not exist. Okay, so that's kind of one area, and it all really comes down to knowing your left from your right. And approaching from the right means coming in from the right-hand side, going towards the number. So you're coming in from the right, go towards the number. And coming in from the left means you start at the left and come in towards your number. We are actually looking for limits at discontinuity, really. This is kind of a good question. What if I wanted to find the limit of f of x here, new f of x? The limit of f of x as x, of f of x. Oh, not paying attention to my own writing. Good grief. Okay, let's try that again. Let's find the limit of f of x as x approaches 3. I want to know what the answer is. So you notice that 3 is a bad point on this function. And you could graph this on your calculator, or you could know how to graph this to begin with. Essentially, I need to look at x squared minus 9 over x minus 3. Some of you are looking at this going, oh, I can simplify this. And then some of you guys are going to get some weird simplifying. But make sure you always factor, let's scratch that. X plus 3, x minus 3 over x minus 3 cancels to an x plus 3. So what this function looks like, and here's where people get a little bit confused. The function x plus 3 is x squared minus 9 over x minus 3. So this looks like this. And on your graphing calculator, that's what it's going to look like. However, at x equals 3, it wasn't available here. So it has to be an open dot there. And then at x equals 3, it's going to equal 2. So it's down there somewhere. So what people get a little bit confused about is this idea of limits. As x approaches 3 from the left-hand side, what is the y value getting really, really close to? And as we approach from the right-hand side, what is the y value getting really, really close to? Well, it's whatever it would have been on the line if it had existed on x plus 3. So I can plug in x equals 3 to figure out what that y value is getting really, really close to. And if I plugged in 3 here, I get 3 plus 3 is 6. That means this open dot is at the point 3, 6. And that is the limit. The limit is 6. The function is approaching 6 as x approaches 3. This coordinate down here is just to define part of the function. It actually has nothing to do with the limit. So the limit is not 2. So you really have to focus on where is the y value going towards as the x value is getting closer to that individual value of 3. All right, let's keep moving here. I believe this is actually the last piece here, the limits involving infinity. We've actually dealt with this quite a bit in Algebra 2, dealing with asymptotes, and I've kind of talked about this before. If I wanted to talk about, in this case, the limit as x approaches infinity, but I can't say infinity because there's two different infinities. Let's say a positive. You don't have to write the positive there. But if I want to say the limit as x approaches positive infinity, or I could ask the question as x approaches negative infinity of 1 over x squared. You basically just ask yourself, actually there's two ways to think about this. One, think about it graphically. Think about what your horizontal asymptote is going to be. And you may know that the graph of this function looks like this. There's a horizontal asymptote at 0, and here at 0, at vertical, and it looks kind of like this. And you may or may not have known that. But here's what I want to ask. Limit as x approaches, I can just think about as x gets really, 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 really big, this fraction is getting really, 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 really small. And so it's getting really, 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 really close to 0. Now you know that it will never actually be 0. But this is the whole idea of some of the stuff in calculus that we have to understand. It may not be getting to equal 0, but the limit of the function is 0. And those of you guys that took biology, you guys know you guys have limiting factors on your population functions, and it's the limit as the population gets really big, it approaches a single value. Well, it goes the same for the negative infinity actually in this case, because as x goes to negative infinity, it approaches 0 as well. And the last piece here is, as x approaches infinity for this piece, you can look at this function as this. This is kind of a cool function because as x gets really, really big, sine of x remains between 0 and 1, and therefore dividing by a big number will become closer and closer to 0. I'm going to wrap this up here. I will see you guys tomorrow.